I call it the Great Hydronic Heist. And I do like this painting. So, question, do you design or install hydronic systems using water-to-water heat pumps? Certainly hydronics up in Wisconsin, Minnesota is very popular. In the Northeast, it's also very popular. Unfortunately, most of our hydronic jobs are with baseboard and oil boilers. So to go in there with a geothermal solution is extremely difficult. But certainly those customers who appreciate the benefits of radiant, then geothermal is frankly a no-brainer. So indeed, we got a lot of experience regarding hydronics. What percentage of your jobs are hydronic? You do predominantly hydronic or a lot of ducted, mixed bag? Interesting, interesting. It is certainly a growing niche that we see. We've been involved with literally well over 100, couple hundred hydronic applications with water-to-water heat pumps, either directly or through our contractors, or just helping design and control hydronic systems. Excellent, excellent. I appreciate the feedback here. Let's look at our industry. And I'm not going to pick on any one manufacturer, but I'm certainly using diagrams that you have might correlate to a specific manufacturer. And I'll tell you, this is right out of the Hydron module catalog. And frankly, I'm a big fan of Hydron module. Let's just examine what they're doing here. There's a buffer tank that we're coming out of a low port, and we're feeding the load, fan coils, radiant floors. We're also coming out of the bottom of the tank, pumping into the heat pump where the water is heated and the BTUs are delivered and put into the buffer tank. And this is a misnomer, storage. We seem to think that a buffer tank is all about storing heat. It isn't. It's simply to prevent short cycling of the heat pump. So you really want to minimize the volume of the tank to be adequate, not because the bigger you make the tank, the more heat loss you got, the more expensive it is. And once again, we're taking it on the chin for pricey geothermal systems when they're not really needed. But when you look at what's driving the design, it is the load and distribution system. It is the radiant floor. How is that designed? It is the fan coil. And by virtue of their inherent capacity and performance characteristics, that will determine the temperatures required. And nothing else really matters. You have to supply a certain temperature water to make these devices perform as needed. So keep that in mind. And in spite of manufacturers telling you what the limit of the heat pump is, well, yeah, that is a limit on the heat pump, but your design, the system, is really going to tell you what you need. Understanding the load. Every application is unique and must be fully understood. Hydronics are probably more in need of good design approach than a lot of other systems. So you really got to look it over. Experience in a specific type of application may allow some seat of the pants estimating, but should never replace appropriate calculations when designing a system. Generally in upstate New York, and I'm pretty sure it's true up in Wisconsin, Minnesota, Residential loads will fall between 11 and 23 BTUs a square foot, with 11 being an extremely well-built, tightly constructed, very unusual building. And the 23 being the older single-story homes. And for the sake of our discussions today, I'm going to pick a load at 18 BTUs a square foot. The 18 is an average for the house. When you go through and do a room-by-room calculation, you will find some rooms at 25 and others at 10. So that's why design is important. So let's pick a corner room. It's got a few windows in it on 2 different walls. 20 BTUs a square foot we need in that room. The room is 20 by 14 or 280 square feet. Our design heat loss turns out to be 5,600 BTUs an hour. However, we've all experienced the polar vortex this year, and we've experienced days that are much worse than design days. So we have to have a distribution system capable of delivering those extra BTUs required. Now, I happen to use 25% more. I'd like to have the capacity in that room of 25% more than my heating design load. Now let's look at different radiant systems. This is staple up. These are your floor joists. You got insulation. You've got PEX tubing. You've got aluminum heater plates, heat transfer plates. You generally get 8-inch on center because your joists are 16-inch on center. You've got your subfloor, and you've got finished flooring. One style of radiance. Typically in a plan view or looking up from beneath the floor, because you can see the floor joist, you will see your PEX tubing going the length of the floor joist cavity, turn around and come back. We've got heater plates as much as we can put in there. And this is not unusual to see radiant designs like this. Let's examine the performance of a typical joist heating, double aluminum plate, 8-inch on center, performance table. We've already factored into this table the resistance of the 3/4 inch subfloor, and we also identify that 120 degrees is the maximum that we should be designing around with conventional water-to-water heat pumps. Now, there's a couple brands out there that can get you warmer temperatures, but they also lose performance like every heat pump. The hotter you make the water, the lower the COP. So I think whether or not you use higher temperature heat pumps, 120 is a good upper limit. A radiant floor at no added resistance, no carpeting, no throw rugs, could give us about 16.5 BTUs per square foot at best with staple up. If you've got resistance or you've lost some of your floor area due to cabinets or whatever, you're more down in the 9 to 10 to 12 range with 120 degree water. Let's look at an above floor system. This one happens to be the Rao panel aluminum track system. There are plenty of other ones out there. Uponor makes one, Warm Board. Above the subfloor system reduces the resistance above the source of heat. And installed, it would look something like this with a 6-inch wide aluminum track, a 2-inch wide nailer strip, and an 8-inch on center design will handle most applications. You can remove the nailer strip and tighten up to 6-inch centers if you needed to get a little bit more out of the floor. From a temperature performance standpoint, at 120 degrees, this particular system can deliver over 30 BTUs a square foot. So let's compare the two. First one, output at 120 degrees with little or no resistance above the floor. I can get 31 BTUs a square foot out of row panel. I can only get 16.5 out of staple up. Floor area, 280. Maximum floor output. The row panel, I can get 8,600 BTUs to heat that room. With the staple up, I can only get 4,600. Now, we determined earlier that our room may need 7,000, and there's nothing I can do to make that staple up system deliver 7,000 unless we raise the temperature. So I need 25 BTUs a square foot. The temperature I need to get 25 out of staple up is 148. The row panel, I could actually turn it down to 110 to accomplish the same thing. And in a boiler world, not a big consequence. But in a geothermal world, that's huge. We're looking at 30% loss in performance just because of the limiting capacity of our radiant design. Fan coils. There's a great number of fan coils on the market. Generally, a cased fan coil like the one on the left. They come with ECM fan motors, nominal tonnages, 2, 3, 4, 5. These neat little smaller fan coils, Airmec, an Italian company, from 1/2 ton to 2 ton. And they also have an inverter-driven fan that is kind of unique, that as you get close to your set point, the fan actually slows down. So you don't hear it turn on, you don't hear it turn off. It just slowly changes fan speed, keeping the thermostat satisfied. Now let's dig into these designs. We're going to control our system with a temperature of the buffer tank. And we got to provide 120 degree water on that design day or lower, but worst case, we don't want to go over 120. So at this point in the tank, we got to have 120 degree water available. And it'll come back from our device anywhere from 100 to 110, depending on your flow rate. What are we going to send to the heat pump? Well, it's pretty darn close to what we're sending to the load. So we're coming into the heat pump at 120, and it'll generate roughly a 10 degree rise, or forcing that heat pump to generate 130 degree water. Another system is B&D Manufacturing, their HSS buffer tank. Great product, does a lot of good things in the marketplace. But again, we're going to end up sending 120 degree water to our load because our load demands it. And we're also going to send 120 to the heat pump, which coming back from the load again is 110. Coming out of the heat pump is 130. Another design, Climate Master. Their THW happens to be a high temperature unit, but you don't make high temperatures without sacrificing COP. But if we wanted to limit it to 120, again, what's coming out of the buffer tank going to the load is essentially what's coming out of the buffer tank and going to the heat pump. I also want to remind everybody, this buffer tank, due to the velocities and the flow rates going in and out, and we're talking 15 GPM possibly to the heat pump, another 10 GPM to the load. A 50-gallon buffer tank is going to turn over every 2 minutes. So there's little or no stratification in these tanks. 110 coming back from the load, 130 coming out of the heat pump. I like this diagram. Another Climate Master illustration. One of the gurus of the industry, John Sigenthaler, I know he uses this software. And it illustrates a little better solution, and we're coming out of the bottom of the tank to go to the heat pump, but we're also coming out of the top of the tank to go to the load. But keep in mind, this color stratification doesn't really exist. Flow rates are much too high to allow that kind of static thermal grading in the tank. So indeed, we're going to come out and go to the load at 120. We're going to go to the heat pumps at 120. We might gain a couple degrees because this configuration is a little better. Come back from the load at 110. Come out of the heat pump at 130. So our entire industry, regardless of who's out there promoting it, has illustrated this type of solution of a single buffer tank, and both the heat pump and the load go in and out. So the question is, why are we sending the hottest or coldest in the summertime water in the system back to the buffer tank where it is mixed and diluted to a lower temperature before we send it to the load? Here's a diagram of what one of our contractors came up with. And after he hit me in the head with the 2x4 a couple times, I said, this is fantastic. Let's look at it. We have to send 120-degree water to the load. Well, why don't we come out of the heat pump at 120, completely bypass the buffer tank, but with a connection to turn it into more of a primary, secondary pumping system, but truly use the tank more as a hydraulic separator and not as a mixing pot. So when we're coming out of the heat pump, some of the flow is going to be available to serve the load, and depending on how many zone valves are open and how our variable speed pump is going to feed those, some of the water that's coming out of the heat pump will go straight to the load. A portion will go back into the buffer tank, and it will just constantly change proportion based on the demand of the load. We're going to come back from the load at 110. This tank is being controlled to 110 because at 110 we can still deliver 120 to the load. We're going to come out of the bottom of the tank at 110, go into the heat pump at 110, come out at 120. It doesn't seem like much, but it doesn't take much to get there either. This design doesn't cost any more. And there's going to be times when the heat pump has satisfied the buffer tank, and we're simply going to draw out of the top of the tank to go to the load. Now, because of the reduced flow rates going into the tank, there may still be a nice little reservoir of hot water at the top of the tank. We draw that down. The tank calls for more heat. We turn the heat pump back on. Let's look at a performance table from this happens to be the Hydron module 5-ton water-to-water heat pump. We're going to look at both 30-degree entering source and 40-degree entering source. We're going to look at the entering load temperatures. They give us 95 and 110. And if we go over to the COP column, 110 has a COP of 2.61. 95 is 3.24. And that same difference occurs at a higher source temperature, which also increases COP. So by being a little generous on the source side, getting loop temperatures up so we don't drive down to 30, and looking at ways to reduce our entering load temperature, we can have a substantial improvement in COP. Doing a little interpolating and taking 2/3 of this difference to illustrate a 10-degree difference in entering load side temperatures. So I'm comparing 100 to 110. 16% improvement. in COP that's available without any significant cost. I want to recognize Jens Ponikow. Some of you may have seen him online at the forums. Doc Jens is his typical name online. Buffalo Geothermal. And really what I want to commend him for is not only his insight, but his generosity. He could have kept this idea to himself, but he has shared it with me and told me I can share it with others. And how about controls? Important strategies to incorporate into any control package you want to come up with. Outdoor reset. You saw the benefit of lowering load temperatures. Well, as it gets mild out, as our outdoor temperature gets warmer, we shouldn't be making 120. We should throttle that down to perhaps as low as 80 when it gets really mild out, and let the control determine the set point based on where you are in the outdoor temperature range. So outdoor reset, I think, is essential. Zone demand. Let the zones dictate when they need heat or when they need cooling, and run your pumps and heat pumps accordingly. The Velostratus pump, variable speed pump. You've got an external off module that you can install right in the pump, and simply by removing a jumper and putting a set of dry contacts to turn on and off the pump. These dry contacts could be the end switches of zone valves. So you wire them all in parallel. If any one of them closes, you turn on the pump. The other way that demand should be incorporated is the heat pumps themselves. Do not allow the heat pumps to run at all unless there is a zone calling for heat. And the way we typically do that is with a Techmark control. They have a boiler demand input terminals, and you could apply a voltage across there. 24 volts, 120 volt, doesn't matter. But when you apply that voltage, it allows the control to turn on the heat pumps. Otherwise, you let the system drift. Our buffer tanks are pretty well insulated. It's going to hold a fair amount of water temperature for quite a while. And then when a zone does call, it won't take long to heat it up because we're only sizing it as a buffer tank, not some oversized storage tank. Hydronic supplemental heat. There are ways to incorporate that in a system. Some folks use an internal electric heater in the buffer tank, which usually has limited output of perhaps 4.5 kW. We happen to have identified an 11 kW inline on-demand heater with a low enough pressure drop for us to use. But either way, you want to impede that supplemental heat from turning on. And the way we've done it is through time delay relays like the one on the right here, and typically 3 to 6 hours. There's enough thermal inertia in these hydronic systems to stretch that delay out to this kind of time frame without compromising the comfort of the occupant. Manual changeover between cooling and heating. This is a hot button. Everybody says, oh, we need auto changeover. I tend to take the position, you give the customer manual changeover, you talk to him about it. If he has significant objections, then you could incorporate some sort of auto changeover control. But you want to minimize the number of times that a buffer tank is dumping residual hot water and chilling it, and then 6 hours later flipping back. So these are just some of our key control strategies that we would encourage you to incorporate. We build them. If it's something we can do for you, here's a job that we did in Syracuse. And and it's controlling this 25-ton completely hydronic residential project, 13,000 square feet. We've got a hot tank, a chilled water tank, and a domestic water tank. We've got hot manifolds and cold manifolds, so any air handler could go into cooling or heating any time of the year. We've got radiant zones that are heating only. This system does 100% of the heating, 100% of the cooling, 100% of the domestic water heating, and we do a little bit of snow melting, so you can't go overboard without adding a whole lot of capacity for snow melting. But it's done without any fossil fuel backup. And that's one thing engineers get hung up on. Oh, I got to have a boiler. I'm sorry. No, you don't. So small difference can make big results. And I've sort of illustrated this before with the difference in performance of a heat pump and going from 110 to 100 and 16% improvement in COP. The bottom line of all three acts here is it is often said that geothermal costs too much. And frankly, I think we as an industry are failing to maximize the value through simple design techniques and fundamental competence in the design community. We can sell the technology at a competitive price and actually deliver outstanding value. I've done several projects where conventional HVAC systems, Auburn City Hall was one, a conventional cooling heating system would have cost them $1 million. Geothermal cost them $1 million. So I don't buy into the myth that geothermal is tough to pay back. I think when they're grossly over-designed, they definitely will not pay back. So I now will open it up to questions. And Jared, if you're still online, I don't know if you've got any. Jared, are you still there? Jared has abandoned me. Pardon me?